All right, so we have two final classes today and also Thursday. And I think no more assessment except for the exam, of course. But I believe your assignment number 4, the due date has been made on the study day. So just make sure you submit. I already gave you guys a solution. You can take advantage of that, but just make sure you still submit because the assignment will still be covered in the final exam. I'll give you guys maybe some PDF guide very soon just to let you know what you can expect for the exam. Okay, I'll talk about it. And also beyond the final week, I will also try to host an office hour, maybe next week and also the week after before the exam. So if you want to speak to me about maybe your previous test or maybe the course material when you're doing the exam prep, also feel free. I'll reach out to you guys about E-class. Okay. And please make sure you also catch up with the makeup lectures. So they are part of the exam coverage. Again, this is where you find them. Okay. So there we go. Sorry. Just make sure I'm more organized. I just want to close this. There we go. Okay. So if you look at the lecture site, you will see that we got the 3 makeup lecture right here. Okay, makeup lecture number 1 and number 2, you can definitely get started. You don't need to wait for any lecture material. However, for the last one there, because the last one there will start with binary search tree deletion. I would suggest only start doing that after today, because today I want to talk about how you can do searching and insertion on binary search tree. I think those 2 operations will give you enough intuition and also ground to really understand deletion. Okay, well, we'll talk about it. Okay, and after today, you definitely want to catch up with all the makeup lectures. All right, and all the materials are there. And then we'll try to see if we can also host some review session during the exam period, right? Well, we can do some maybe survey just to see which time I work for you guys in person, okay? All right, any question about the course? Your programming test number 2, we are grading it. I do know next Monday is another deadline for some of you. You may have some consideration or decision to make. I'll definitely make sure the feedback and the result will be available to you by next Monday, the latest. Okay, the latest. I think the TA is now grading it, but I think on schedule. Okay, let's do a quick recap, and they'll continue with binary search tree. Things will get more and more, a little bit deeper, but I think it's also more and more interesting about the stuff we're going to talk about. All right, let's now start with some quick recap. In order to define a binary search tree, so it's really about binary tree plus the search property. And search property goes like this. Whenever you're given a tree, over here, for every internal nodes, you want to make sure, let's say for this internal node, which happen to be the root, every node in the left subtree has their key value strictly less than the root key value. And also every node in the right subtree over here, they have their key value strictly larger than the root key over here. So you think about binary search tree stores an entry for every node. Each entry has the key and the value. And typically for our discussion about mathematical property, we don't really cover about value because this part here is completely up to what you want to store for your application. It's mainly for the key. That will be for searching. And on Thursday, in our last class, we're also going to touch upon another topic called heap. It's just another kind of binary tree, but a little bit different from binary search tree. In that case, we also assume every node stores an entry as opposed to a single value. Just make sure you understand the assumption here. All right? And that's one way to really check for the search property. You can just check for every internal nodes. Okay, that's one way. The other way is about thinking about the so-called sorting property. So sorting property is really a consequence of 2 things. One is about the searching property we spoke about for binary search tree, and also for the in-order traversal, which we know is only applicable for binary tree. So if you try to do an in-order traversal on a binary search tree or some candidate tree, you're not simply sure if that would be a binary search tree. Do an in-order traversal, if somehow you get an increasing order of the key value, you will know that it's a binary search tree. All right? It's a very important property to know about as well. It's more like a lemma. It's something we can derive, from the main search property. And okay, that's good. All right, so that's a page where we try to show you the one-to-one correspondence. Think about the binary search tree we're given is actually nonlinear. And then after we have done the in-order traversal, we get a linear sequence of the keys. Apparently, it's in the sorting order, in the ascending order in this case, because keys have no duplicates. So it cannot be non-descending. It has to be strictly ascending. So in this case, we kind of showed to you about a one-to-one correspondence. For example, this is the root 44, which is right here. The in-order traversal or the linearized version of the left subtree goes right here in this left, like a subsequence. And also the in-order traversal for the right subtree goes in this right subsequence. Right? So you can see the one-to-one correspondence for even smaller subtree, for every subtree basically. Okay? So we did an exercise as well last time. And another important exercise, especially this will be very important when we do searching, even more the case when you guys study the makeup lecture for deletion. Because you want to know, if I want to search something, or I want to insert something, what kind of node should I really choose to replace? And the replacement should be done in such a way that we can still preserve the search property, which means the resulting tree should still be a binary search tree. I'll make it more concrete once we get there, right? I want to mention that first. So we talk about, given this particular binary search tree, let's say for this particular node, right now it is 76. And accordingly, we identify the predecessor and also successor of the corresponding in-order for traversal. So we say that right now is actually valid because 76 is exactly between 65 and also 80. So the question is, what value can we replace 76 by? It should be any value that's in between 65 and 80. For example, it can be 66 all the way to 79 inclusive. Right? So that's the range of key value we spoke about. We want to make sure the search property for the binary search tree will be still preserved after the replacement. And this is a very important property to keep in mind because when we do insertion and also for deletion, you have to make sure this is something that's preserved. Guys, are you okay with this about predecessor, successor? Okay, that's important. All right, good. All right, that's just another example. All right, so this one here, just make it a little bit more generalized. If you got some node here, you got left child and right child, and then we got identify several nodes, right? So just talk about if you do in-order traversal, this will be the minimum of the whole tree, and this will be the maximum of the whole tree, right? And the root over here will be somewhere in the middle. If you see the corresponding in-order traversal sequence, that's what it is. Especially, let's say for P here, right? You can see the node that goes right before that. Because we know everything on the left subtree is guaranteed to be strictly smaller than the key value for the root. And then we know that the rightmost node right here is the maximum for the right subtree. So now we are having some very special place for this node here. That one there, first of all, is a left subtree. So it must be smaller. At the same time, it's also the maximum amount all the nodes that's strictly smaller. Right? That's how we phrase it. Symmetrically, every node in the right subtree right here will be strictly larger than the root for the key. However, this node here happens to be the minimum, even though it's the minimum for the right subtree, but it is still strictly larger than the root because it's in the right subtree. All right, so these two nodes, be careful, they are very important. Especially when you study for the deletion, it's really about whenever I want to delete some node, in some case, I may have to replace my node either by this or this. You have option, right? Just keep that in mind. You will see that thinking question I posed to you in the makeup lecture. All right. Are we okay with this structure here? Good. Good. All right. And then we talk about how you increment binary search, especially BST node. So we talk about between internal nodes, creation, and also external node. I know some of you might still be confused. Why do we know? Why do we need to have like external nodes explicitly right here? There's a reason. Okay, once we talk about searching operation, you will see exactly why. You can have some advantage. Beyond this course, of course, if you want to implement your own binary tree or binary search tree, you don't necessarily have to make such distinction. I'm kind of following some like a textbook standard, so which many people are adopting. But if you really want to make only one kind of node, only internal, external, the same, that's okay too, right? But for this course, we make that assumption. All right, either external or internal. And then we talk about how you can implement in-order traversal recursively. I'll encourage you guys to really try pre-order and post-order traversal as well. You should just be able to reorganize the recursive call a little bit to make it work. That can even give you some more insight about the difference between different traversal mechanism. Okay, I'll leave that to you. But the source code is already on the lecture site. Okay. All right, and then this test case, just about if you do in order traversal for this binary search tree, you'll get exactly this order, 21, 28, 35. All right. All right, any question from last Tuesday? All good? Okay, so let's now build on top and go further. Let's start with the searching operation, right? So I would suggest we try to do the searching visually before we look at the Java code, because Java code corresponds to exactly what I'm going to do visually. Let's do that and build the intuition, and then we can look at the Java code and do some tracing together. So there are basically two cases for searching. Let's write it down first and outline our expectation. So when we are doing searching, there are basically two cases. By the way, the searching we are doing for BST is not simply just a Boolean, like a true if we have found it, or false if we have not found it. Not really. We always return a BST node. However, the kind of BST node we return tells us whether the searching has been successful or unsuccessful. So that's something I want to visualize to you. Okay? So for example, one case would be I'm looking for 65. As you can see, 65 is here. On the other hand, 68 is not here. However, when 68 is not here, we should still return something. But what exactly should we return? All right, that's the question. Okay, we'll get there. So for the searching result, either successful or not successful. Could be successful, which means the key we're looking for is there. In that case, we simply return the internal node that stores the key value. For example, here, we're looking for 65. And we're going to return just this internal node that stores 65. Okay, that's this case, but I'll visualize even more. And the second case is about if the key doesn't exist, what should we return? The short answer is because there's no such internal node that will store the key value we're looking for. Right? You can see, for example, 68. There's no such internal node that will store simply 68. For example, here, it's not simply a 68. So what should we store? The idea is you want to return some external nodes, and that external nodes will represent the right place if I wanted to insert 68, which currently does not exist, but we'll see. So here, this will be unsuccessful. Unsuccessful. Okay, in which case, return the, let me put in quote, the right or appropriate external node. I will see exactly what I really meant by being appropriate. The right external node. Right in the sense that it's going to preserve the in order traverse, it's going to preserve the search property if we were to insert 68. Okay, let's look at first case over here. All right, so here we're looking for 65, so that's a key value that we're looking for. We'll start with the root right here, okay? And then, let me use highlighter, that might be easier. So we start with 44, right here. And then we compare this key. So it's really almost like doing a binary search on an array, almost like it, okay? So what we do is compare 65. We know 65 is larger than 44. So that means it must exist in the right subtree. That's exactly the search property. Anything larger than 44, if existing, must be in the right subtree. So we'll go to the right. As soon as we go to the right, we are essentially truncating the search space on the left subtree. Okay? So what we do is, this part over here is not applicable. So we don't even go there. So what we do is, we go to the right here. All right? And now we compare 88 and 65. And 65 is actually smaller than 88. So go to the left. So if we go to the left, that means we can truncate exactly this right subtree. Okay. So we go to the left subtree right here, and then we're lucky. We have found it. All right, so we have found it, and then we simply return this internal node storing the matching key value. All right, so that's the successful case. Question about this before I say something else? Okay, so now, one thing to see. When we decide to go to the right or go to the left symmetrically, we essentially are forgetting about the other branch. We can do that safely because of because of the search property. Okay, so here we go there because of the search property. So if you recall, in the binary search for the array, if I got an array that's exactly sorted, and then the way to do it is we go to the middle right here. And if I decide to go for the right half, I am pretty sure I can essentially truncating the other half, which will be exactly n over 2 versus n over 2. So that's why we get a log n, like a running time for binary search for the array. However, for binary search, it may not be the case in general. Say, so what I want to mention, I'll make it more general a little bit later, but I want to say for this part over here, this part is no longer included in the search space. Another question is it always going to be like a n over 2 that we are forgetting? If it is, that's good. Then the searching will just be like a binary search on the array. Not necessarily, okay? That's something I want to keep you in mind, right? I want to give you some intuition, okay? So here, the answer is not necessarily. Can be big O of n, in which case n over 2, or in the worst case, maybe just a constant. For example, you can see that when we actually decide to go to the left, this part over here seems to be pretty small. It doesn't seem to be balanced with this one here. Apparently, this, as far as this node is concerned, is really left heavy. So when we truncate the right, it's not going to save the running time too much. So in general, when you're doing a search on the binary search tree, there's not really guarantee about how efficient it might be. There will be some little constraint you have to watch out for. Well, I'll talk about it. All right, so far we talked about the successful search, right? And then you just return the internal node that has the matching key. Okay. So now let's talk about unsuccessful. Okay. Very similar idea, very similar. So what we do is, let me start with 44. Again, start with 44. And 68 is larger than that. So we go to the right, the same as before. And of course, we truncate the search space right here. And then we also try the 88. And 68 is strictly less than that. So we go to the left. And we have truncated the right subtree. Okay, now we are 65. And 68 that we're looking for is larger than that. So we just go to the right. Okay, and there we got 82. 68, again, is less than that. 68 is less than that. So we simply go here, and then we get to 76. We still haven't found it. So keep going, right? Until you either reach some external nodes, or you have reached a node that has the matching value. So here we got 68, also less than that. And now we are reaching this particular external nodes. As soon as we have seen an external node, we know that we can no longer go to its left or right. External node simply got null as the left and right child. As far as the searching is concerned, you're going to just return this external nodes. However, why this particular external nodes? Return this external node. The reason we want to return this external node is, usually, as we'll see very soon, the searching will be part of the routine if you want to do insertion. Whenever you want to do insertion into a binary search tree, you should always start with a search. And then the search can either succeed or fail. And then, accordingly, the insertion will be done a little bit differently. In the case where, let's say I want to insert a new node into this tree, and the new node must have 68 as the key. If I return this particular external nodes, what would be good? The good thing is, if I put 68 here, and I still want to do in-order traversal, I will still get a sorted sequence. To be more precise, accordingly, think about the question. I'll put a question here, and then identify the answer. Okay? What are the predecessor and successor of this external node? Remember last time we talked about predecessor and successor. Now we are applying that idea. All right? So, as far as this external node is concerned, you can do the exercise again later. This would be the predecessor. And the successor will be right here. If you do the in-order traversal, you will do 54 and then 65. After that, you will get to these external nodes. And then you get to the root, which will be 76. That's a successor. Okay? Let me just put it here. Let's say this is external nodes. You can think about the external node will be in the middle, and then we got 65 that goes before that, and also we got 76 that goes after it. So this will be the in-order traversal. All right? So you can double check about in-order traversal. I'm going a little bit fast because I can assume you guys will know how to do in-order traversal. So you can double check to see the sequence, especially for this part. It's going to be 65, followed by this external nodes right here, and then followed by 76. So now the question is, what can we insert within it? Right? Anything that's in between 65 and 76 will be okay. So now in this case, if I want to insert 68, I can also do it if I want to. Okay. We may insert 68 right here. So this really answers about maybe some common question from last time. Why do we have to distinguish between internal node and external nodes in the binary search case? That's because whenever you want to do insertion, which will involve searching, and whenever you want to do searching, if the search is not successful because the key does not exist, you want to ask, if I do want to insert this non-existing key later into the tree, where should it go to? And the idea would be you want to put it in the external nodes where the predecessor and successor will simply just bound it in the right way so that you still maintain the sorting property. Okay. Guys, any question about this? Anything? Yeah, go ahead.
So about the O-abandoned and O-avoid.
Sure.
So like if we're told that the binary tree we're given, the binary search tree is complete or full, can we assume that it's always going to be O and over?
It's a very good question. Yeah. So you're talking about some special case. The special case is if I know the binary tree is binary search tree is also either complete or full. Yes, the height will be log n, because we know the full binary tree is the maximum case for the number of nodes. Accordingly, the height will be the minimum case, which is log n. That one also previews about what we're going to study for heap data structure. Heap is simply a special binary tree where one of its property is complete. So once you get to the complete tree, you always got log n. However, the problem is, given it's an arbitrary binary search tree, we don't really have, if you don't have any assumption about that being complete, then you cannot make that assumption, right? Yeah, we'll get there. Okay, guys, what I can summarize, I think your fellow student made a very good point. Okay, over here, if a binary tree is complete, so that means the height is big O of log n. All right, so that's something you can also take a notes. Okay? This is something we also touch upon when we talk about heap on Thursday. All right, let's now do some very quick Java tracing just to see about searching, right? So now this is a JUnit test case. That's also part of the example code I gave to you. Let's now stop this part here. It's just about like what we said last time, about how to create the nodes in isolation and also set up the child and parent references, right? For that part, we can do quickly. That's something we already did last time, okay? So for this part here, you can think about we got 1, 2, 3 nodes. So this node is N28. This node is N21. And this node here is N35, right? And also we got 4 external nodes. 1, 2, 3, 4, okay? Accordingly, this will be external node number 1, external nodes number 2, external node number 3, and also external node number 4. The same setup as before. And for this part here, it's just going to set the parent and child references. For that part, I'm going to omit just for now, right? We did that tracing last time. You can double check. What I want to focus on will be, there will be searching in this particular binary search tree. I want to compare successful case versus not failing case with you, okay? But you can look at others as well. I will also encourage you to really run this code here in debugger, in Eclipse. The code is already there, so you can definitely give it a try. So let's look at this one here. I'll make it a bit thicker. Let's look at this, this line here, first of all. That one there, we're looking for, let's see here. We are looking for 21. So we're doing a searching operation. And we're saying that we want to start with the root, which is the starting point. Okay, we'll start with that root. And then we're looking for the 21. This is the key to search. And that one there is simply just going to go from, basically go from here, 28. And then we know that 21 is less than that. So we go here. And also 21 is right here. So that should be returned. All right. So that's why for this one here, you will see N21, the reference is equal to exactly the return value from the search method. Okay. So think about this reference is returned when searching for 21. And if you look at the other two cases, will be very similar. If I'm looking for 28, if I'm looking for, let's say, 35, I'm going to return this node right here. If I'm looking for 28, I'm going to return the reference for this node. They're all existing. Successful search. Successful search return the reference of some internal nodes. How about unsuccessful search? For that one there, let's take a look. So let's look at this one here. Okay, I'll make it pink. Maybe better to read. This one here. Okay. So let's say we're searching for the key 33, which does not exist. 33. And we still start the search from N28, the root. We still start from here. And then 33 is larger than 28. So we go to the right. And 33 is less than, oh, let me just write better. 33 is actually less than 35. So we go to the left, right? So the way to go is we go here first, and then we go here. And we are reaching this, we have reached this external nodes. So that means this is the external node to return. Okay, let me write it down. This is the reference to return when searching for 33. Because in a subsequent insertion, which we'll see in the next page, 33 will go right here. So think about searching doesn't really come just by itself often. Usually we'll just do insertion or deletion, right? So insertion will be part of it will be searching. So that's why we want to return just the external node so they can convert it right away. Okay. Any question about Java code here? Any questions? Okay, take a look at that. Hopefully it's not too complicated, right? You just have to distinguish between successful versus non-successful. Each one of them is going to return some reference. You just have to know whether the reference will be the reference for some internal nodes or the reference for some external nodes. So that's the difference. Okay. All right, let's now talk about a little bit more how you implement the search, and then some running time discussion. Okay. Okay, so guys, if I'm doing too fast, please do stop me, right? Okay, so this is the search method, and you can see that the search method here is, okay, it's a recursive method, first of all, because you can see that the search, the method itself can call itself either here or here. So it's a recursive method. And you can see that we also got the return value. Not a Boolean, either true or false, it's a BST node. And we can make some nodes right away to remind ourselves. So the BST node here will be the reference of some internal or external node. And let's analyze the code a little bit, and then we'll talk about runtime, okay, which is critical. So we just have some temporary variable here. The result, eventually we want to return it. So there are different cases we got to consider. Okay. Case number one. If the current node that we are looking at is external, pretty much like when we were searching for 33. And then we reach the external node right here. That's the first case. In that case, we know that it's unsuccessful. Just return the external nodes. Right? So the P here is some external nodes that we're returning. Okay? Also, it's unsuccessful search. All right, that's case number one. Okay? You can think about once you reach the leaf, like external node, it's a base case. And base case number two. If the current node that we're looking at is internal, and also it has a key value, and the key value matches the key we're looking for right here. So we know that we have found it. So this will correspond to this case right here. When we were looking for 21, we are returning the reference for the 21 as soon as we have found it. Okay. So this case over here will be the P, that being internal node. So these are the only two base cases. Either we have found it or we have reached the bottom of some external nodes. On the other hand, we got two recursive cases. Either we go to the left or go to the right. Right? Let's look at them, and then we'll talk about runtime. So this will be recursive case number one. Recursive case number one. this will be recursive case number 2. So R1 will be the key of, let me put it this way. When the key you're looking for is less than the key of the current node, that means you want to recur on the left subtree. That's why you saw it here. Right? Recursive case number 2, the key you're looking for is larger than that. So we know that it can only be on the right subtree. The key you're looking for is strictly larger than the key for the current node. That means you're going to recur on the right subtree. And one more thing to note. In general, left subtree and right subtree, they may not be exactly balanced in their size in general. But let's keep this note here. That will impact the running time. Okay. Left subtree, right subtree. In general, may not be balanced in their sizes. It could be that maybe one side has only one node. The other side has n minus 1 node. In that case, it's completely ill-balanced. Okay? It depends. Now, let's now figure out the running time. Okay? The most intuitive way to think about it is, let's redraw the tree. Right? This is a diagram you will actually just see in the slides. But let's be a little bit more critical here. Okay? Be logical. Because whenever you want to talk about search running time for any general binary search tree, there are 3 different ways to express. Right? Let's talk about all 3. Let's now start with the tree first. So let's say this is the tree I'm searching for, searching the key for. Okay? Let's say here, this is the root, of course. So the search starts from here. Okay? We talk about some binary search tree. Okay? That's a setup. Search in general, we know that either we can go to the left or we can go to the right. Every time we go to the left or go to the right, we're going down one level. Right? Let me write it down. It's very critical intuition. Okay? Get left or get right. If somehow this is not explicit enough for you, I will just give you a quick notes. I'm now currently at level 0. Either I go to the left or go to the right, I'm going to go to level 1. So every time I say either get left or get right, down one level. The question is, how many levels should I go down until I can return? Either because of a successful search or unsuccessful search. That's a critical question. All right? So I can keep going until I reach, okay, keep going, okay. So each get left or get right moves down one level. So what's the worst case running time? Depends on how many levels you have. Agree? Okay. So keep going until we maybe have found we can conclude the case. So the running time goes like this. There are 2 parts to consider. We have to, first of all, compare. Right? You can see that here we have to compare about whether the key we're looking for is either less than or larger than. Right? Either way, we want to compare. We have to compare the K. Number 2, we have to move to either left or right. So the running time really depends on how many levels we should really move on. We should really move down. Depends on the number of levels required to explore. the key. In the worst case, maybe you have to simply move down all the way to the very bottom level, which will correspond to the heights of the tree, right? So think about the worst case. Worst case would be h, the height of the tree. The height of the tree, if you remember, it corresponds to the maximum depth of the node. How many links, parent link, do you have to go from that particular node all the way to the root, right? So that will be the worst case. This is one way to express. Okay, so now we're going to express the running time. Okay, I'll put it here. Running time by version 1, big O of h. So the search operation on a binary search tree is simply going to be proportional to the heights of your tree. Because every time you move down, it takes only big O of 1 to compare and also to really get left and get right. But just about how many levels should you really travel? That'll be exactly h. So this will be the most accurate way to say things in terms of the h. So this is the accurate. However, sometimes people, if you know more about the tree itself, maybe the tree is very balanced, or maybe the tree is not very balanced, then you may want to express the running time rather than in terms of h. You can express that in terms of maybe n, the number of nodes, right? So now we get A2 and version 2 and version 3 as well. So running time version 2 and also running time version 3. But it is really something we already covered in the binary tree lecture. Okay. Again, let me just say one more thing here. Big O of h. Okay. I will need to refer you back to something we learned earlier. Okay, I'll put it here. Revisit. When we say given n nodes in the tree, and we say that the h has some lower bound and also upper bound. Okay, so there's a number here. There's also some number over here. That's what we spoke about earlier, right? Well, actually, that should be quite obvious, right? Do you remember? What's the lower bound? No. Well, that would be nice, wouldn't it? Log n. Okay? The lower bound here is log n, and here the upper bound is n. Right? Guys, you can double check, right? That's something we learned earlier. You can definitely review the derivation that we spoke about earlier. But I'll dive directly to quoting the facts. So here, it could be big O of n, or it could be big O of log n. And this is correspond to, this will be when the tree is balanced. And we'll talk about what I really meant by balanced a little bit later today. Oh, I beg your pardon. Because big O of n is really the worst, right? It's really, it's not balanced. I beg your pardon. Okay, it's not balanced. On the other hand, the big O of log n, when the tree is balanced. Let me make a quick recap about this page here, and then we'll take a short break. Okay. So we spoke about the Java implementation for the search method. Notice that the return value here, return type, is not just a Boolean. It's actually some BST node reference, depending on successful or unsuccessful. And we spoke about base cases and also recursive case. If you think about it visually, every time you want to make a recursive call, you either go to the left or go to the right. And so that means every recursive call will make you one level down towards the bottom of the tree. So that means the number of recursive calls you have to make is really bounded by how high the tree is. Because the height of the tree is defined by number of links by the parents go all the way to root. Okay? So that's why there are three ways to really specify the running time for that. Either you can say the most accurate way, just say it's going to be corresponding to the height of the tree, big over h. But we know before, given n nodes, the heights can be either lower bound, big of log n, or it can be the upper bound, big of n. So that's why these are the another two. If you know more about the structure of the tree, whether it's balanced or not, you can say, rather than big of h, you can say either this or this. It really depends. But I'll give you more example after the break. Any questions about this? All good? Okay. Why don't we take a short break, and then we'll resume. All right. I want to give you guys more concrete example about when you do a search on the binary search tree, depending on whether the tree is balanced or not. We're still not getting very formal, just to give you some example. But for these two binary search tree number 1 and number 2, but I can verify that each one of them is a binary search tree. You can do it in order traversal. You will just get the same in order, the same sorted sequence. So binary search number 1, binary search number 2, if you do in order traversal, you will get the same sorted key right here. All right, that's something I'll leave as exercise for you. That's very easy to verify. On the other hand, I want to show you that this binary search tree over here is more or less we call balanced. Okay? We also introduce about what I really meant by balanced more formally a little bit later today. Let's get some more intuition. On the other hand, this binary search tree over here is not balanced. You can say unbalanced. Let's give a little bit more justification. Okay? So here, if you count, the number of nodes in the tree is 15, right? Of course, this one here as well. The number of nodes is also 15. Their contents are the same, just the structures are different. However, the heights for this tree here, you can see this is more like the bottom node. You got 1, 2, 3, 4, 5 links. So the height is 5. So roughly about big O of log n. Because log 15 is like a 4, close. Okay. So this is one thing to know. So you might have a very good case where the height of the tree is log n. That means whenever you want to do search, the worst case would be you just get log n. It would be that many levels you have to traverse all the way down. Okay. On the other hand, this tree here kind of got split into two halves exactly, and each half over here either is completely right slanted or completely left slanted. Okay. So the right hand side, the height is actually 7, which is about n over 2, which we know is big O of n. All right. Because you see that the number of nodes right here is about half of the tree, and it's completely slanted. Okay. And the height here is about, you can just count 1, 2, 3, 4, 5, 6, 7, right? Just about big O of n. Let's say we want to do some searching, okay? If I want to search, let's say, let's start with the balance tree. I start from here, and then let's say I want to search for 80. Searching for 80. And I want us to really observe the correspondence between searching on this particular binary search tree and searching that same key in the array. They more or less correspond to each other, about truncating half of the search space every time, right? We'll see. So searching for 80 on BST number 1, more or less the same as performing a binary search on array A. So let's say this is array A, the in order traversal of the tree. Right, let's see. So we start with 44. And 44 is here. And we are searching for 80. So we should go to the right. So we basically go to the right. And we have reached 88 right here. And 80 is less than that. So we go for 65. So we definitely should go for the left-hand side right here. Right? And then get to 65, which is right here. And compared with 65, 80 is larger than that. So we go to the right. And we get to 82. Right? That means we're going to go to the right. Right here. Okay, I'll go a little bit bigger. So we're going to go right here. Okay. And then we go to the 82. Yeah, we'll go to 82. Beg your pardon. And then we'll get to 82, which is right here. Okay. Once we get to 82, we have to go to the left. Okay. We go to 76. And then we go to 76. And then eventually, we know that we go to 80 right here. Right here. So that's how we have found it right here. So the main thing I really want to show to you is this. Every time we go to the right, go to the left, etc., it's really like doing a binary search in the array, because if we go to the right over here, we are truncating the left half of the array. Essentially, we're truncating left subtree, and etc. Right? So this performance over here is going to be more or less log n for the searching. I want you to see that correspondence. On the other hand, when you do the second binary search tree, let's say we're looking for 97. Searching for 97, which is right here. It's more or less a linear search on the array A. So we're talking about a linear search versus a binary search on the array. So think about whenever you're doing a search on a binary search tree, in the best case, you can pretty much get a binary search on a sorted array, which would be log n. But in the worst case, it will be as if you're doing a linear search on the corresponding in order traversal sequence. So let's see that quickly. We start with 54, and then we go to the right, we go to 65, right? We're looking for 97. And then it's always bigger than that, so we always go to the right. Go to the right, go to the right, go to the right, and eventually we reach 97. So if you look at the corresponding part in the array, we start with 54, right here. And then 65, right here, and etc. It will be corresponding to just like a linear search. Eventually we get to 97. There's no like a truncating this search space like what we have seen in the first case, right here. Are you okay with this example here? So we're just saying with different structure for your binary search tree, you might just have different performance. But we have to make sure we define more formally about what it really meant by balanced versus unbalanced. That's something we have to see how to calculate systematically. But at least get the idea. Okay? Any questions about this? Okay, if no, let's do one more operation for binary search tree, which will be insertion. And then we define what I really meant by a tree being balanced. Okay. So this page here corresponds to, so we talk about searching. And then running time for the searching. You can also look at more closely at slide number 14. So here I also talk about the different versions for stating the running time, right? That's what we spoke about before the break. That'll be slide number 14. You can take a look. And let's talk about insertion. That'll be starting from slide number 15. For insertion, you always start with a searching routine to see whether the node I want to insert, does it exist already for the key, all right? And if you look at the parameter for searching, this will be the key I want to insert. And the associated value I want to reinsert will be just a string value, let's say. So this will be the value. Okay? So always the first step for insertion starts with a search. So what I will do is I'm going to search for 28 from here. Okay, let's assume you know how to do searching, so I can speed up the process. So 28 should go to the left first. And then I go to the right, and then I go to the left. So this will be 28 right here. All right, so I found it. So I return this note as the search result. So here, so step number 1, searching 28, searching the key value 28 returns, let's say this is our internal nodes. Let me call it N. Reference N. And all I need to do is, I know the key exists, but I want to make sure the corresponding value is updated. So second step, whatever N that's got returned is not null, right? It's never null, either external node or internal node. In this case, it will be internal node. I want to set its elements to be whatever this value it is. So that will be, in this case, 3. So always start with a searching for insertion. Whether or not the key exists, that's okay. You always got some reference back. All right, let's talk about second case. Let's say now I want to insert a new entry with a key 68, which does not exist in this current tree, which I know is I'm going to get a reference back, which is will be the external nodes. I'm going to convert that external node into internal in one moment. Okay, let's see. So what I do is I'm going to start with the root, and I'm going to search for 68. Let's see where that external node should be in order for me to do insertion. So I start with 44, and then I go to the right. And 88, I go to the right, left, right here. And then 65, I go to the right. 82, I go to the left. And then 76, I go to the left. So this is the node that will be returned. All right? That's kind of the exercise we did earlier, so I'm just speeding that up. Okay? So this external node will be returned. This is the external node that's returned. And let's be more precise about what's going on here. Let's call this EXT, the reference. Okay? So what we had was step number 1, searching 68, searching the key value 68 returns the reference EXT, which will be this external node. And conceptually, we're going to convert this square external node into a circle internal node. Okay? You can work out the Java detail. So think about EXT. Currently, it's pointing to this external node right here. What I do is I can try to turn that into internal node. And that internal node should store the 68 and also the value here. So that'll be 68 and also UNA over here. And of course, every internal node, that will be the bottom internal node already. So that means the left child and also right child should also be external. Right? That's what you have to do. Okay, let me recap. When you want to do insertion, the most critical step would be phase number 1. You want to do a searching. And the search may either return some existing internal node that contains the search key. In that way, just modify the value. There's no new objects you have to create. On the other hand, if the key you're searching for does not exist in the tree at the moment, in that case, find out the corresponding external nodes by the searching routine, and then convert that external node into internal, and set any parents and child references appropriately. Okay. Of course, when I say convert, you have to make sure you also set the child and parents references accordingly. Just for example, this external node used to have the parent reference pointing to 76. So when you create this new internal nodes, its parents should also be the parents of these external nodes, right? For example. So that's the Java detail you have to work out. Okay. Any question about insertion? So up to this point, you're ready to learn about deletion. All right. So after today, you can definitely plan your time to catch up with the deletion lecture. All right. So this will be the last part for the binary search tree lecture, right? So you can see that we are done with the insertion here, and those are the two examples we did. And the last topic will be the deletion, which is the makeup lecture, right? I'll let you follow it, and that'll be it for this lecture. All right. So let's now start with the final slides for the course. Okay, we're going to talk about priority queue, heaps, and also heap sort, right? To start with, let's see what we will learn in this lecture. Okay, we'll talk about the so-called height balance property, but I will just want to revisit one more time just to see how we can result in the worst case running time for search, in which case the height of the tree will be just linear, big O for n. Okay, and we'll talk about height balance property. That's something I'll show to you how you can calculate. And then we'll talk about priority queue. It's a new abstract data type, just like a stacking queue, right? You just got a new way of thinking how to manipulate the data. And then we'll get to some implementation that may not be so efficient, and then we'll get to the more efficient implementation for priority queue, like a heap data structure. Okay? And then we'll talk about heap sort as well. That'll be the last topic. So we'll cover these also on Thursday. Okay. Let me start with over here. Okay, you can look at slide number 3, but let me just get to the point right away. Okay. I'll do example number 1. You guys can try it out. Example 2 and 3 exercise. Okay, I'll put them down first. Okay. For these two examples, you can leave them as exercises. Okay. You just want to see, after inserting all these nodes, what will be the heights for the resulting binary search tree. Heights. Is it n or is it log n? Is it big O of n or big O of log n? Okay, that's an exercise for you to try. But let's try one of them. So the question goes like this. Start with some empty binary search tree. We want to insert these keys one by one in this particular order. Okay. So when we do the first one, 100, it will be just right here. Okay, the first node. That's the root itself. And then we try 75. So 75, we know that should go to the left of 100. And then we try 68. That should go to the left of 75. And then 60. That will go to the left. And then we go to 50. And we go to 1. Of course, to make sure we draw completely, and this one here has external nodes, and the right child is also external. The right child external, right child external, right child external, and left and right child external. So that'll be completely consistent with our convention. Okay. So now for this particular tree, it's completely left slant. Left slanted tree. Okay. What we are interested is about the heights of the tree. Okay, the height of the tree will be a maximum depth. The height will be 1, 2, 3, 4, and 5. All right. So it will be just about the number of nodes. So if you want to do a searching, what will be the worst case? Well, let's say if I'm searching for, let's say node 1. In that way, I got to go all the way down to the bottom here, and the height is already linear. So that will be the worst case running time for binary search because the tree itself is not balanced. Okay. The tree is not balanced. So what we want to do now is to define more formally a property to say, in order for us to really have log n heights for the tree so that we can get efficient insertion, deletion, and also searching, what should be the property we want to satisfy, right? That's something we want to go over. So we'll talk about a new lecture here, right here. So the one we just did, it was right here, right? Slide number 3. And then let's talk about, this is just a recap, like a brush up about the heights for any node. Height for the tree. There's a new property we want to talk about. It's called a height balance property. Let's look at the formal definition first, and I'll show you how you can calculate. It's actually rather straightforward if you want to calculate it visually. Okay? It goes like this. It's a recursive property, like a search property. Whenever you want to check to see whether a binary tree given satisfies the height balance property, for every internal nodes, you want to check the heights for its child nodes and look at the difference. If the difference is less than 1, less than or equal to 1, then it will satisfy. If there's any internal node that would not satisfy this property here, you will say that the tree is not balanced. Okay? But let's now look at an example right away. So try to look at the definition textually, in the textual definition before Thursday. Okay, so if you got any question, you can ask me. But let's see exactly how we can calculate it. Okay, I'll show it to you. I'll do 2 examples with you, and then you can do one more. The remaining one is exercise. Okay, let's see. Let's start with here. This one here. So is this tree balanced? We'll ask the following question. And the way to check it is we want to check the height balance property. Height balance property. Yeah, sometimes you'll see acronym in the slides or maybe in the test question. Okay. Let's now try to calculate bottom up the heights for individual subtree. Okay. We'll calculate depth actually. So let me just annotate here. Compute the depth of nodes bottom up. All right, so that's the critical step to remember. Okay, let's see how we can calculate it, right? For external nodes, by definition, the depth will just be 0. Okay? The height will just be, let me just see this one here. Let me modify this a bit. Beg your pardon. Let me change this. Sorry. Let me annotate first, and then I'll get the textual remarks right there. Sorry about that. Okay. So we start with the external nodes. And then we're going to put simply 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Simply because when I get some external nodes, we're saying that the heights of a subtree rooted at external nodes is, by definition, 0. Okay? And then what will be the heights for this node? It should be the maximum heights plus 1. Okay. So 0, 0, and then maximum will be 0, and then plus 1. And also 0, 0, maximum will be 0, plus 1, I get 1. So the heights for this subtree over here is 1. And the heights for this right subtree is also 1. Okay. And what will be the heights for this subtree? It will be the maximum and then plus 1. So that will be 2. Okay. So also good? Okay, let's do. Before we can figure out the heights for here, let's look at the right-hand side here, the right subtree. So we got 0, 0, maximum is 0, plus 1. I get 1 here. 0, 1, maximum is 1, plus 1, 2. 0, 0, maximum 0, plus 1, I get 1. So now 2 and 1, maximum 2, plus 1, 3. So 2 and 3, maximum is 3, plus 1, I get 4. So always try to annotate the heights for individual subtree first. Okay? Annotate heights for subtrees. And number 2, you want to look for violation. Look for violation of the height balance property. So what do I mean? You basically want to compare the height difference. So for example, if as far as this node is concerned, I compare the difference between these two heights. Okay, over here. So the difference over here will be 1 minus 1. Okay? 1 minus 1 is less than or equal to 1. So it's okay, no violation. And I also look at the heights for these two nodes, these child nodes. And then I got 2 minus 1. The actual formal property is saying that you should really take the absolute value, because you can also say 1 minus 2 and then take the absolute value. Right? You can do either way. And the difference is also less than or equal to 1. So that one also satisfied. Okay? Finally, you can look at 2 and 3 over here. I can say the difference 2 minus 3. And then that's also less than or equal to 1. So check for all of them. So there's no violation. Let me repeat, and then we'll do one more example. Whenever you want to check for the height balance property, first of all, annotate the heights for every node bottom up first. And then you look for violation. The way to look for a violation is for every pair of the siblings, you look at their heights and what's the difference. If the difference is more than 1, then that'll be a violation. If the difference is less than or equal to 1, there's no violation. Let's look at the second question here as an example. Is the tree balanced after inserting 55? All right, let's take a look at that. 55, we should really go all the way to right, left, right, right. Right, 55. According to insertion, we're going to convert this node into internal, which will be 55. Underneath it, we got 2 external. Okay, let me draw better. So think about we got 55. Underneath it, we got external. So after this insertion, we're actually going to annotate the heights for every node bottom up. Let's do the same exercise. Right? 0, 0, 0, 0, 0, 0. External will be the same, just 0. That's always the starting point. Okay? So what will be the height for 55? 0, 0, maximum, 0, plus 1, I get 1. What will be the height for 51? 0, 1, maximum 1, plus 1, I'll get 2. Okay? Height for 48, 0, 2, maximum 2, plus 1, 3. Okay? Also 77, 0, 0, maximum 0, plus 1, I get 1. Okay? 56. 3 and 1, maximum is 3 plus 1. I get 4. All right, that's the right-hand side. You may have seen some violation already, but I'll get there, okay? So 0, 0, I get 1. 0, 0, 1. 1, 1, I get 2. 2, 4, maximum is 4, plus 1, I get 5. All right, and let's now look for violation, okay? How many violations do you see, for example? For this branch, do you see any pair of siblings whose height difference is more than 1? 1 minus 1 here is the difference 0. So there's no violation on the left. But how about here? What kind of violation do we have? I'll make it a little bit larger. So if you look at 0, 1 over here, the difference is if I do absolute value, 0 minus 1. Oh, sorry. Give me 1 minute and I'll be done. Okay. So somehow my Apple Pencil got disconnected. Give me 1 moment. Okay. Huh. Sorry, guys. You know what? Somehow my Apple Pencil just got disconnected, so I cannot really write. How about this? Let me stop here and then think about this property here, and then we'll just try to finish this example as the first thing on Thursday. So we got one more lecture on Thursday, so you can now definitely start with the makeup lecture on the BST deletion. All right, thank you so much. I'll see you on Thursday.